Most people think of NIST as a federal laboratory that only works to improve measurements, but its true central mission is to enable innovation. But how does a measurement agency support innovation? Well, if you know how to measure something, then you can begin to think about how to design it, to build it, and to make it better. And these capabilities really are the essence of technological innovation. Measurements permeate every aspect of our lives, from how we make things, to how we sell things, to how we regulate things. And NIST measurements give us a way to know we can trust this system to be accurate. Today, the technologies that are most important to us are not single standalone technologies. They are actually systems of technologies that need to work with each other. And how they work together is defined through standards. In the United States, standard setting is led by industry, but NIST plays a critical role in supporting, defining, and fostering that effort and coordinating it with the federal government. NIST's role among technical agencies is unique in many ways. Over our long history, we have cultivated deep scientific roots that cut across a whole range of disciplines. Having such strong and varied scientific expertise without being a regulatory agency is what allows us to work so closely with such a broad spectrum of industries and other government agencies. And NIST cooperates with similar organizations around the world to make sure that the system of measurements we use here works on a global scale. So when you think of innovation, think of any technology around you. The odds are that NIST played an essential role in making that happen.
The National Institute of Standards and Technology, NIST, has released an urgent report to aid in the defense against an escalating threat landscape targeting artificial intelligence, AI, systems and identifies types of cyberattacks that manipulate behavior of AI systems. The report considers the four major types of attacks: evasion, poisoning, privacy and abuse attacks. It also classifies them according to multiple criteria such as the attacker's goals and objectives, capabilities, and knowledge. Evasion attacks, which occur after an AI system is deployed, attempt to alter an input to change how the system responds to it. Examples would include adding markings to stop signs to make an autonomous vehicle misinterpret them as speed limit signs or creating confusing lane markings to make the vehicle veer off the road. Poisoning attacks occur in the training phase by introducing corrupted data. An example would be slipping numerous instances of inappropriate language into conversation records, so that a chatbot interprets these instances as common enough parlance to use in its own customer interactions. Privacy attacks, which occur during deployment, are attempts to learn sensitive information about the AI or the data it was trained on in order to misuse it. An adversary can ask a chatbot numerous legitimate questions, and then use the answers to reverse engineer the model so as to find its weak spots, or guess at its sources. Adding undesired examples to those online sources could make the AI behave inappropriately, and making the AI unlearn those specific undesired examples after the fact can be difficult. Abuse attacks involve the insertion of incorrect information into a source, such as a web page or online document that an AI then absorbs. Unlike the aforementioned poisoning attacks, abuse attacks attempt to give the AI incorrect pieces of information from a legitimate but compromised source to repurpose the AI system's intended use. There are theoretical problems with securing AI algorithms that simply haven't been solved yet. If anyone says differently, they are selling snake oil.